Hello grade 10s and welcome to this week's lesson on trigonometric functions. Now for many people, trigonometric functions starts looking like a foreign language, like maybe you're learning Greek or something. But they're actually not that bad. In fact, I would say of all of the functions that you do this year, trigonometric functions are the easiest to grasp. You're just feeling apprehensive because it feels like we've done a whole lot of other functions over the last few weeks and you're starting to feel scared. But I want you to put those fears aside because you will love how easy this is. Now, just to get you into the mood, we're going to look at the challenge question for today. And remember, you need to take it down so that when we do the 3 challenge questions from the last 3 lessons next week, you'll be able to check your answers against mine. So let's take a look at that challenge question, and I'm going to read through it with you. It says, consider the graphs of the functions f and g. Write down the domain of g, of theta. Okay, what is the amplitude of f of theta? Determine for which of theta f of theta is equals to g of theta is equals to 0, and g times f is less than 0. And remember, that's a fancy way of saying you're going to get a negative answer when you multiply the 2 values together. And when g divided by f is more than 0, and remember, more than 0 is a fancy way of saying you're going to get a positive value, and where f is an increasing function. Now, let's just highlight for you, f is starting down there, going up to 3, going through 180 and down to -3. That's for f. And then for g, we've got this other function. Now I wonder how many of you have recognized these functions already. Which one is which? And I suppose if you've been doing trig functions in class already, then you would know them already. Okay, take a minute to copy this down, and then we will see you just now. Okay, so now that you've got that down, let's start talking about what a trigonometric function is. Now you'll remember that a function is a relationship between 2 values, and a graph is something that we can plot. Now in a function, we only ever have one output for every input we have. So in your your algebraic functions like your straight line and your parabola and hyperbola and exponential graph, when we substituted one value in for x, we could only get one possible value out for y. Now with trigonometric functions, we're talking about the relationship between the ratio and the size of the angle. And I'm going to go to our first slide for today, which talks about the key concepts and has this in mathematical language. It says a trigonometric graph shows the relationship between the angle and the ratio. The sine and the cosine graphs are very similar, that's very true, but the tangent graph has some asymptotes. And you'll remember from previously that an asymptote is a line which the graph continues to approach but never ever touches or crosses it. Okay, but let's go back to this first part. A trigonometric graph shows the relationship between the angle and the ratio. And let's talk about that a little bit. Here is a triangle. Now on this triangle, we've got various values, and whatever the values would be. Let's call this R, and let's call this Y, and let's call this X. Now if we have theta down here, we would say that sine of theta is equals to Y over R. So this fraction is our ratio. Remember, ratio is another word for fraction. And theta would be the size of the angle. Okay, so the ratio and the angle are the two measurements that we're looking at, the relationship we're looking at. Okay, so that means when we just start plotting it, we're going to use the angles that we have in functions or in the trig functions. So let's say we find sine of 30 degrees. We're going to find out what that is equals to and plot that point. So what do you think the input value is? Well, in this case, our input value is going to be theta, because we put sine of theta or sine of 30 degrees into the calculator and we're going to get an answer out. Same thing with cosine. We would put cosine of, and remember cosine is the long version of cos, so maybe cos of 62 degrees. And we would find out what it's equals to, what the ratio it is, or the number is equals to, and then we would plot it on the graph. Now with the sine and the cosine graphs, they both look very similar. They've both got a bit of a wave pattern like this. But the tangent graph then has points where it cannot exist. And that's why we have asymptotes with the tan function. And when we get to the tan function just now, we'll talk about that a bit more. But first we're going to look at the sine and the cosine graph. Now grade 10's, the trick with this is to learn how to plot that parent function. If you know how to plot that parent function, you'll be able to do any problem that you're presented with. And the parent function is the function that we have before we make any changes. In other words, the function would be y is equals to sine of theta, or x is equal, not x is equals, y is equals to sine of theta, or y is equals to cos of theta. Okay, let's go and look at the parent function of the sine graph. And I have a graph already set up over here. I'm just going to write over here what we're going to do. Y is equals to sine of x. Now, because I've done this many times before, I know exactly what points I'm going to plot. And I'm going to put one over here. And you should be able to plot these without thinking. Now, I realize grade 10s that I have not explained anything. All I've done is drawn an upside down and to the side S, which is nice to help us remember the shape of the sine function. So it starts at 0, 0. It goes up to 1 at 90 degrees. And then at 180 degrees, it comes down to zeros again. Now, let's use our calculator to prove that I am correct. I'm going to take sine of 180 degrees. Oh, let's hit the buttons. 180 degrees and press equals. According to my graph, it should give me an answer of 0. And so it does. So this point over here is 180 degrees and 0. where sine is equals to 90. Let's check if I was correct. And we're just trying to go back to the calculator. Sine of 90 degrees, close our brackets, press equals is equals to 1. So once again, I'm correct. At 90 degrees, sine of theta has a value of 1. Let's try at 45 degrees. So sine of 45 degrees, close our brackets, equals square root 2 over 2, and that is 0,7. Am I correct? Well, this is roughly 45 degrees over here, and that looks roughly correct. So grade 10s, I have memorized the shape of the sine function, and I've drawn it up and down and then up again. Does the sine function end at 360 degrees? Now, if you've been doing this in class already, you would now be telling me, no, it doesn't. It doesn't end at 360 degrees. The sine function actually continues to go up and down forever and ever and ever. We just choose how far we're going to draw it. There's a reoccurring pattern that happens though. If it goes up to 1 in the first hill, then in the next hill it's going to go up to 1 again. And if it went down to -1 in the first hill and hole, then it's going to continue to go down to -1. Okay, now one of the reasons this happens, and let's continue this graph going down over here, is because we can continue to go around the Cartesian plane. You'll remember from when we did trig earlier on this year, we had the cast diagram. And over here was 0 degrees, and then we had 90 degrees up at the top, and 180 degrees, 270 degrees, 360, squeeze that in. Then it carried on going around until it became 720. And then it would go around again, and it would become 1080 degrees. We could go around for an indefinite period. Just carry on going around and around and around, and we would still be able to get the same angles. Now, you'll remember that sine was positive both in the first quadrant and in the second quadrant. What do you notice about the function between 0 and 90 degrees? It's above the x-axis, which is also theta in this case. So that means sine is positive in that quadrant. And of course, between 90 and 180 degrees, it's also positive. So we have positive, positive in the first and the second quadrant. But then we go into the third quadrant. And what happens in the third quadrant? Well, only tan is positive in the third quadrant. And look at that. The function is below the x-axis, which means it is negative. And it's negative in the fourth as well. Now, if we look on the other side of the y-axis, we know that negative 90 degrees is going to fall into this fourth quadrant. And according to our cast diagram, the fourth quadrant is negative, where sine is negative. And look at this. Over here, it's negative. So our graph is really illustrating what is happening on the cast diagram as well. Okay, so just to recap before you take a break, the sine graph starts at 0, 0. Okay, the sine parent graph starts at 0, 0. Then it's going to go up to 1, and it reaches 1 at 90 degrees. Then it goes down and goes to 0 again. And that happens at 180 degrees. And it goes all the way down to -1 at 270 degrees, and then it goes back up to 360 degrees. It has one complete pattern in the space of 360 degrees, and we call that a period. It also has a height of 1 unit and an amplitude of 1 unit. Now we're going to go over these terms again as we do the cosine function, but before we get into that, it's time for you to take a breather. We'll see you soon. Okay, grade 10s, welcome back. Now we're going to look at the cosine function. You'll remember that I mentioned two important words before the break, and that was period and amplitude. Now the period is the amount of time it takes one cycle to complete. And that's kind of like the amount of time it takes one pattern to complete. So if we thought of it, actually let's draw on this. I'm going to use my cosine graph paper, and I'm just going to draw a pattern. And here we go. The pattern's going to be triangle, circle, triangle, circle, triangle, circle. And I think we can all agree that my pattern is just a bunch of triangles and circles. But if I wanted to reduce it, I would say that it is a triangle and circle that's been repeated how many times? There's another repeat, and here's another repeat, and here's a repeat over here, and another one over there. Now each one of those is a cycle, one cycle. How long does it take for one cycle to complete? Well, if we look at the graph, we'll see that it takes 180 degrees to complete one cycle. And this is true for every single one that's happened. Now the same thing happens with trig functions. A period is the length of time, or degrees, that it takes to cover one cycle. And in the sine graph, it was 360 degrees. I'm just going to get rid of all of my drawings here. There we go, like magic. And let's start with the cosine graph. Now, once again, I'm going to draw the basic cos graph, and then I'm going to prove to you that I'm right. So it's going to start at 1, go down to 0, then to -1, then up to 270, and up to 360. A trick I've learned over the years is to draw these graphs in different stages. So you'll notice I'm drawing each quarter on its own, and then I'm lifting my pen. It just makes it easier to get the curve right. Okay, now this is the standard cosine function, and it, like the sine function, is going to continue indefinitely. Carries on and on and on and on. Forever and ever and ever. But let's talk about the period of this. How long does it take to cover one cycle from there to there? The period is equals to 360. Period 360. It's just like the sine function. Let's go back to that sine function and take a look. Oh, I made a big mess, didn't I? But look, the period is also 360. Do you see any other similarities? Did you notice that the sine function also goes up to 1 and down to -1, and also has a wave-like shape? With our cosine function, and the computer's just taking a while to decide to move for us, it also goes up to 1 and down to -1. Now, we call this measurement the range. What y values does it cover? We would say the range is between -1 and 1. In other words, y is an element of, and we're including -1, so it's straight brackets, and 1. its domain, well, it's going to go on forever and ever. So we would say the domain x is an element of any real number. If I had been asked, there we go, if I had been asked to only draw from, let's say, 0 to 270 degrees, then that question would have said only draw from x is between 0, so we're including 0, and we're including 270 degrees. And that would mean that I would stop my graph over there. But I'm not going to do that now, so let's just get rid of that. Oh, put my bracket back in. Okay. Now, the other thing we need to talk about is the amplitude of the graph. The amplitude is from the center of the graph up. What is the height? Now, the height is something different. I can have, let's put some space down here. I could have a function that starts up here and goes down and then goes up. Let's say it starts at 2 and goes down to 0. In other words, my range is from 0 to 2. Whoopsie, I'm getting very untidy. But anyway, and my height has a measurement of 2, but my amplitude is not 2, because my amplitude is looking at where would that center point be. And from that center point up, I still have an amplitude of 1. Okay. Now, just in case you're wondering what the equation of this graph is, as you can see, it's still a cos graph. Let's just make it clear that it still has a period of 360 degrees. It's still a cos graph, but instead of starting at 1, it now starts at 2. And instead of going down to -1, it now goes down to 0. So what we've done is we've just shifted our cos graph up by 1 unit. In other words, we've just added 1. How do we shorten the period? Well, I can show you the easy way to do it, and that's just to draw it shorter. So let's do a straight line there and a straight line there. And so instead of, and let's just draw a cos graph in, and instead of having it end at 360, let's cheat, scribble that out, and have it end at 180 degrees. Now, what does that mean the middle point over there is going to be? 90 degrees. And what is the new period of this graph? Well, it's now going to be 180 degrees. Remember that the period of the graph is the amount of time it takes for the cycle to complete. So yes, this is going to continue going on and on, but the pattern happens in 180 degrees. Now, the equation of this graph is going to be y is equals to cos 2x. And if you think about it, that kind of makes sense, because if we extend this line, what would this value be over here? It would be 360 degrees. So how many cos graphs have we fit into this space? We've fitted 2 into them. And look, there is the 2 over there. It's like magic. It really, really is. Okay, so let's go on to the tan graph and talk about it for a little while. Now you'll remember that tan is equals to opposite over adjacent. Now that means that we may have a problem, because we can never, ever, ever divide by 0. We can't, so our adjacent value can never, ever be equal to 0. Whoopsie, it should be tan of theta. Now, If we do it on the Cartesian plane, we would say tan of theta is equals to y over x. So that means x must never, never equal to 0. But we're not doing it like that. Now we're looking at the value of the whole ratio versus the value of theta, where theta is the input. Oh, I'm making it nice and untidy. And the ratio is the output. So, let's go back to our calculator, and I will show you what I mean. Now, because I am clever at this, I know that tan of 45 degrees is going to equal 1. Let's look at it. Yes, it does. So I'm going to plot that point over here. And let's go back to our calculator and plot tan of 0 degrees. And it's equals to 0. Do you want to guess what tan of negative 45 degrees is? Let's see. Tan of negative 45 degrees. And we press equals. It's equals to negative 1. Now let's see what tan of 90 degrees is. Close our brackets, equals, oh dear, math error. Now what that means is that when we have tan of 90 degrees, we no longer are able to get a mathematical value because our adjacent value would be 0, which means we're dividing by 0, and everyone knows when you divide by 0, the whole world explodes. Or it starts raining pigs or something, I don't know. Basically, it cannot be done. So that means the tan function or the tan graph will never ever exist at 90 degrees. Now we mark that point with an asymptote, and an asymptote is a dashed line that we just put in just to show that the tan function is going to carry on getting closer and closer to it, but it will never ever touch it or cross it. So it is important that we mark that down. I'm going to do that now. So at 90 degrees, and you would of course use your ruler to do this, I'm putting in my dashed line, and I'm going to label it at the top as x is equals to 90 degrees. And then I'm going to draw my tan function. Once again, starting in the middle and going down. Now, why am I going closer and closer to negative 90 and not touching it? Well, let's see what the value of tan of negative 90 is. Also, math error, which means we have another asymptote over here. So, I hope you agree with me that this is then the length of one pattern. So that means our period is equals to 180 degrees in a normal tan function. And this is y is equals to tan of x, or tan of theta. Okay, I'm going to draw the other ones in. Goes down like this, and it goes up like this, with another asymptote coming all the way down, and once again goes down. And let's go over here. It's going up, closer and closer, but never touching, and going down. And then we've got our asymptote. So you get the general idea. Now, if we wanted to reflect this function or any of the other functions, can you guess what we would do? If you said we would multiply it by a negative, you would be correct. To reflect it, it would be y is equals to tan, negative tan of x, or negative tan of theta. And let's extend the page. And let's look at our calculator. Now, if we go and we'll do negative tan of 45 degrees, we're going to get an answer of negative 1. which means in this new graph, at 45 degrees, we've got a value over there. And then if we go negative tan of negative 45 degrees, negative 45, oh, let's get our 5 in there and close our brackets, we get a value of 1. So that means our graph now goes like that. And we have our asymptotes. Okay, grade 10s, it's now time for you to have a bit of a breather, and then we're going to start doing some problems. Now remember that you just need to know what the parent functions of all of these look like. And sine and cosine, they're pretty much the same. The one starts at 1 and the other one starts at 0. And then tan just has those asymptotes. Okay, we'll see you just now. Welcome back, grade 10s. We've got a couple of minutes left so we can get a few questions done now. Remember that the sine function starts at 0, 0, and it looks almost like an S that's been turned on its side. And the cos function starts at 1 and 0, or 0 and 1, and comes down and then goes up. So it almost looks like a C that's also on its side. Then the tan function, well, it's just that lucky one that looks different. And the reason it looks different is because it has those asymptotes. The period is the amount of time that it takes for a function to repeat its cycle and go over and over again. And the period for the sine and the cosine are both 360 degrees. But the period for the tan function is 180 degrees. Now, the amplitude for the sine and the cosine function, it's both equals to 1, and that's in the parent graph. In the tan function, it just goes on forever and ever and ever. So we can't actually even tell what the height or the amplitude is going to be. So we don't ask that question because no one can really tell. It goes on for infinity. Now that's an interesting concept, infinity, but it's not one that we have time to explore at the moment. We're going to start by looking at a plotting the function type of question, and then we're going to go into the more typical types of questions that you'll get. Now with the plotting the function question, I'm going to teach you a trick to doing it, and it's all got to do with remembering how the parent functions look. So our question says, draw a sketch graph of y is equals to tan theta plus x. So let's just y is equals to tan of theta plus 1, and it's asked for only the domain between 0 and 180 degrees. Now I know already that my tan function, normal tan function, is going to start at 0 and go up and up and up and up, and the asymptote is going to be at 90. And then it's going to at 180 and in the middle over there. But that would be if it was just y was equals to tan of theta. And this is y is equals to tan of theta, but I don't need that. I need to add 1 to it. So what happens when I add 1 to anything? Like 2 plus 1 equals 3, or 76 plus 1 equals 77. Now in this case, what is 0 plus 1? Well, it's going to be 1. And over here, what happens to that point? It would also move up 1. So that means instead of being at 180 degrees and 0, it's going to be at 180 degrees and 1. So all of our points are moving up by 1 unit. That's the only thing that's happening. And it's that plus 1 that's important. Now I have a feeling we have graph paper, there we go, on this slide over here. So I'm going to draw in the tan function, and then I'm going to shift it. So I'm first drawing in the function y is equals to tan of theta, and it's going to start at 0, and then at 45 degrees, meet 1. Whoopsie, I'm sorry, it's not the best looking line. Okay, and now I'm going to pick it up with my arrow, and I'm just going to move it. You see how I'm moving it? The whole function is moving up. And there we go. Instead of being at 0 and 45 degrees, it's now at 45 degrees and 2. And over here, it's at 0 degrees and 1. So I've added 1. Now let's do the same for the bottom. It would have come up to 180 degrees after coming from down there. But that's the parent function, and we don't want the parent function, we want the parent function plus 1 unit. So I'm just going to move it up by 1 unit. And there we go. So if we go back to this, that point over there is going to be what's halfway between 90 and 180 degrees. It should be 135 degrees. So 135 degrees and 0. And then this point over here is going to be, any guesses? 180 degrees and 1. Are our asymptotes still in the same place? Yes, they are. Now, we were only asked to draw the function between 0 and 180 degrees. And look, there's the question over there. It says theta has a domain of between 0 and 180 degrees. And that's how we know to stop at 180 degrees. Okay, grade 10s, that wasn't so bad, was it? And you can see how easy it is. You just take your parent function and then you make a change to it. So if you're adding 1, then your parent function, whether it's sine, cosine, or tangent, moves up 1 unit. If you're subtracting 3, then your parent function is going to move down 3 units. If you're multiplying the whole thing by a negative, it will just flip. And if you are multiplying x by a number, it's going to stretch or expand the graph. You'll be able to fit that many cycles into the normal period. Okay, now sketching the function is usually an uncommon question in mathematics. What we tend to do in tests is ask you to interpret functions. So the next few questions focus more on the skill. And once again, you just need to know how to interpret the parent function, and that means you'll be able to do fine in these questions. Okay, so let's take a look. Sketch the graphs of f of x is equals to 2 sine x and g of x is equals to cos x minus 1 on the same set of axes for the domain of 0 to 360 degrees. Okay, so that is actually the first part of our question. The second part of our question says use our graph to determine f of 180 degrees, g of 180 degrees, and then g of 270 degrees minus f of 270, the range of g, and the amplitude and the period of f of x. Now, I know a lot of you are looking at this and going, eek. But it's time to turn that frown upside down, because once we've drawn those functions, all of these are going to be easy peasy. So we don't have to worry about these now. In fact, take those worries away, because once we have these pictures, we'll be fine. And the trick to drawing these pictures is to think of the parent graphs. Now, the parent graph of a sine function is that s that goes up and down. And usually it has a period of 360 degrees, and it goes up to 1. But this isn't the parent graph. This says f of x is equals to 2 sine x. What are we doing to the sine x? Well, we're multiplying it by 2, which means instead of going up to 1, let's cross it out, we're going to go up to 2. And instead of going down to -1, we're going to go down to -2. Is the period still the same? Yes, it is. So it's still going to be 360 degrees. It's still going to go up first and then down. So other than that, we're fine. So I'm going to start by drawing the sine function in. And they want us to only draw for a domain between 0 and 360 degrees. So once again, I know that it goes up to 2 at 90 degrees, and then it's going to go down to 180 degrees, and let's just scroll down a bit so that we can see the rest of it. It's going to go down all the way and then over here as well. Not the prettiest, but it will still get me my marks. Okay. Now the second graph we need to draw is g of x is equals to cos x minus 1. We know that the cos function, parent function, starts at 1, goes down to -1, and then up again. It has a period of 360 degrees, and that's really all we need to know about it. But this one is moved down one space. So we're going to change the parent function by just moving it down by 1 unit. So instead of starting at 1, we're going to start at 0. And instead of going down to -1, we're going to go down to -2. Does it still have a period of 360 degrees? Yes, it does. So not many changes have happened. Just to make our lives easier, I'm going to draw it in a different color. And then let's do it in pink, one of my favorites. It's going to go all the way down to over here. And it helps to mark the points just so that you have a more accurate graph, especially because the next answers we have to do, we've got to read off our graph. Okay, so I've drawn the two functions in. G is our pink graph and F is our purple one. Okay. Now, because I can see into the future, I know the next slide has our questions repeated on it, so let's go look at them. Use your graph to determine f of 180 degrees. Now, you know from earlier that it was f of x in the graph, but now we've replaced x with 180 degrees. So this question is asking, when x equals 180 degrees, what is y? Okay, and the reason we write it like this is because mathematicians are lazy. We don't want to write out a paragraph. That's a paragraph. So we rather write down things in function notation. So this is function notation, and it's just a much easier way of writing things down. So when x is 180 degrees in the f graph, what is y equal to? Let's go back and look. Okay, in the f graph, when x is 180 degrees, y is equals to 0. That was easy. So we just write our answer as f of 180 degrees is equals to 0. Like I said, easy. Okay, the next one says, when g of x is 180 degrees. And that means, what is the value of y when x equals 180 degrees on the g graph? Let's go back. And the g graph was the pink one. And we look over here. At 180 degrees, g is equals to, or y is equals to -2. So let's write that answer in. At g of 180 degrees, it has a value of -2. Now this is where most people start to panic. G of 270 degrees minus f of 270 degrees. Well, let's treat them as two different problems first. Let's find out what g of 270 degrees is equals to and what f of 270 degrees is equals to. And we go back to our graph. At 270 degrees, f is equals to 0. And at 270 degrees, g is equals to, oh, not 0. Helen, read it properly. At 270 degrees, f is equals to -2. And at 270 degrees, g is equals to -1. Now I can actually figure out, using these two values, what the difference is between those. But let's do it mathematically. So we've got -2 and -1 as our two answers. So let's write them in. G of x was -1 and f of x was -2. I'm feeling unconfident, so I'm just going to look again. I'm pretty sure I'm right. And f at 270 degrees was -2. Yes. Okay. So that means this question, C, is asking -1 minus -2 is equals to what? Well, this is now a grade 8 problem, so I know you'll get it. There's a difference of 1 unit. And when we look at the function, we'll see, let's go back, that there is actually a difference of 1 unit between those 2 points, between this point and this point. Now the next question asks for the range of g. Okay, so g was the cos graph. And let's go and look at the cos graph. The cos graph starts at 0 and goes down to -2. So those are the y values, possible y values it can be. So I'm going to write down y is an element of, and it starts and includes -2 and goes all the way to 0. Then the amplitude and the period of f of x. The amplitude is the height from the middle point. Now f goes up to 2 and it goes down to -2. So that means it has an amplitude of 2, because from the middle point of the function up is 2 units. And then its period, the amount of time it takes to cover one cycle, is 360 degrees. So let's write those in, and then we're done. And it really wasn't that bad. So the amplitude had a value of 2, and the period had a value of 360 degrees. Okay, grade 10s, next week we're going to tackle some really interesting questions with interpreting functions, and we're going to do a more complicated version of all of our functions, algebraic and trigonometric. So I'm really excited, but until then, keep practicing, keep going at it. You can do this. It is not scary. It really, really isn't. I'll see you next week.